Intermediate test model. Backbones and counting. We ended the last discussion with finding the largest gap, twice the current prime minus 1, in an ESM, and explored some of the consequences. Now we turn our attention to the study of tuples, and show there exists deep quantifiable structure. We begin with using the fact the gap set of SM is periodic, and notice if we add the set to itself shifted by one member, we simultaneously sample all gap pairs. And though it is trivial, it is nonetheless remarkable that in any SM, the average of all pairs of gaps is twice the average local gap size. Of course, this trivially generalizes to the average span of a tuple of n gaps as n times the local average gap. This prompts a predictor function we call the backbone of the modular form. It is the expected count of members below some value. Let x equal to 1 plus j times the local average, or rather, j, the index, is the floor function of Rx minus 1 divided by R local average. Define capital L of M at x, the lumbar function, to be our above form, the floor function of Rx minus 1 divided by the local average. This is exact and periodic as follows. The local lumbar at x plus any multiple of the current primorial is the local lumbar at x plus R multiple times our current first minor primorial. The lumbar has several other features. The lumbar at any multiple of the current primorial is R multiple times our current first minor primorial, and the local lumbar at x plus the local average gap is the local lumbar at x plus 1. That is, in the context of the backbone, the local average gap is of unit length. In S0 and S1, the gap sets were degenerate, but after this, they develop deep structure and randomize. In a beautiful sense we still have addition by 1, except now 1 is a random operator, our local average gap. The gaps are performing a random walk, except instead of steps of unit length and random direction, we have a single direction and a random step length. The distribution is also clearly not uniform, and it clearly has memory via the SRRs. The S-model is not a tool, in and of itself, to study the prime numbers. For example, it's missing the first 10 primes. They are encoded in the sense of the primorial, but they've been tossed aside into what we call the midden. They are the ashes of each Big Bang, expansion, and the composite killing machine. Because the primes are split into the separate sets, we can't really take limits. The two sets talk about different things. We can, however, consider primes and gap tuples however large we wish. Consider the following. Here we examine the local lumbar at x plus the expected value, but now we do so at the square. Moreover, we are interested in the differences at the square. A little manipulation of the definition gives us the following. That is, our difference at the square is about twice x. While appealing to the PNT, our result is exactly twice what we expected. We stress once again, the S model is not the PNT. The local average gap is constructively the mean for SM, and SM doesn't know that in this region, the PNT forces the average gap to be twice as big. Nor does it know, for example, around X being near the current primorial, the real average gap is of order the current prime. The set as mentioned earlier is primarily polluted by composites, and the local average gap must represent the entire set. Asking the same question using the PNT, we get the expected difference is half as large, because the average gap has actually grown to be twice as large. That is, on average, we expect about our current prime number in count in this region. We wish to analytically continue the backbone, so we begin with the natural constraint. Our backbone at the next guess, minus our current estimate, should equal 1. Performing the standard Taylor expansion, we get the first derivative of the backbone at x equals 1 over the log of x. However, we also need to solve the second condition to ensure we concur with the PNT, that is, at r square must equal Rx. Fortunately, it has the same Taylor expansion. That is, the analytic continuation of the backbone is the special function, the logarithmic integral, or Li, of x. That is, our backbone function is the best possible estimator of the S model. So by construction, the function, the logarithmic integral, the backbone of the primes, is the best possible estimator of the primes. That is, the expectation between the prime counting function and its backbone is, on average, 0. Consider Chebyshev's theorem and the S model. Trivially, the next prime is 1 plus the sum of all the prime gaps below it. Replace the local real gap with the local expected average, and we get the next prime is 1 plus the sum of the natural logarithm of the prime numbers less than r number. If we had used the local average operator, the result would be simply scaled by these power gamma. Now, let's look at the same structure at the square. Our next prime squared is 1 plus the sum of the differences of successive prime numbers squared. But the well-known differences of squares can be split into an antisymmetric product. That is, this reduces to the sum of successive primes times the gap between them. But the next prime is also the current prime, plus the current real prime gap. A little manipulation and we get the final exact form. Using the same trick, we get a new Chebyshev form, that is, Rn(x) prime squared is approximately 1 plus twice the sum of the current prime times the natural logarithm of the current prime plus natural logarithm of the current prime squared. Or for large primes we get the next prime is approximately the square root of twice the sum of the product of the current prime and the natural logarithm of the current prime. We refer to Chebyshev's function as the A form, and this second function as the B form. Each form tells us something different about the primes. The A form tells us that at the local scale around x each gap is unique, while the B form says, given x at x squared, the gaps appear uniform in length. This proves to be deeply profound. In the next video, we will take a close look at the Hardy and Littlewood prime gap distribution model. We show it is a natural structure of the S model, and so constructively true. We also show this implies distributional resonances, and go on to generalize their model further. For more information, please see the next lecture, or Google multiplication modulo n along the primorials, with its differences and variations, applied to the study of the distributions of prime number gaps.